Welcome to this video on digital electronics. This video, which is the fourth in the series of combination logic circuits, we will be discussing about encoders, decoders, priority encoders and magnitude comparators. First, let us consider encoders. Encoders are nothing but combination logic circuits that have 2 power n inputs and n outputs. So, the inputs can be 2 power n or lesser than that, and there are n output lines. The encoder generates binary code for the given input value. Examples of encoders are octal to binary, decimal to BCD encoder, priority encoders and so on. Let us take an example of octal to binary encoder. So, octal means 8. So, there are 8 inputs ranging from D0 to D7 and the 8 inputs can be represented in binary using 3 bits from 000 to 111. So, there we have an encoder with 3 outputs. So, the encoder is an octal to binary encoder which has 8 input lines and 3 output lines, and it is assumed that at any one given instant only one of the input lines is enabled, and for that input the corresponding output is obtained. So, let us see how to design the encoder. So, first draw the truth table. The given inputs are from D0 to D7 and the outputs are Y2 to Y1, and at a given instant only one of the inputs is high. So, for D0 high the output is 000. When D1 is high the output is 001. For D2 high it is 010 and so on. For D7 high the output is 111. Now, the logic expression for the same should be obtained. So, we can observe from the truth table directly Y2 is high for the values of D4 or D5 or D6 or D7, and similarly Y1 is high for the values of D2 or D3 or D6 or D7, similarly Y0. So, the logic expression is given and from that the logic diagram can be obtained. So, using OR gates the octal to binary encoder is designed. Pause the video, design a decimal to BCD encoder. So, the inputs are decimal numbers, it can range from D0 to D9 and the output is BCD encoder. So, BCD can be represented using 4 bits. So, proceed with the design. So, this is the truth table for the decimal to BCD encoder, 10 inputs and 4 outputs, and the output is high corresponding to which of the inputs are high, and this is the logic diagram for the same. Next, priority encoders. So, in the previous slides we saw only one of the inputs is high at any given instant of time, but that might not be the case. More than one input could be high at any given instant. So, priority encoder, it includes a priority function. So, if 2 or more inputs are high or are logic 1 at the same time, the input that has the highest priority will take precedence. Let us look into this with an example of a 4 input priority encoder. First, let us draw the truth table. The inputs are 4 inputs D0, D1, D2, D3, and the outputs are 2 outputs Y1 and Y0. So, it is enough if we can represent 4 inputs or 4 unique values with 2 bits in binary. But then we include another output line called valid output indicator. So, in this example D3 is considered to have the highest priority and D0 the least priority. So, the precedent goes from D3, D2, D1, D0. So, D3 has the highest priority, D2 next, D1 next and D0 the least priority as given here. And V, which is a valid output indicator, so it is set to 1 when any of the inputs are 1. And if V is 0, it indicates that none of the inputs are 1, that is all the inputs are 0. So, when V is 0, the value of Y1 and Y0 need not be looked into. So, here look at this, when all 4 are 0, valid output is 0, and so the Y1 and Y0 values are don't cares. Now, we will go from here. D3 has the highest priority as indicated here. If D3 is high, then irrespective of the values of D2, D1, D0, the output is 3, that is 1 1 in binary. And similarly, if D2 is high and D3 is 0 in that case, D2 has higher priority compared to D0 and D1. So, the output is 1 0, that is 2, and if D1 is high and D2 D3 is 0, in that case the output is 1 irrespective of the value of D0, and if D0 is 1 and all others are 0, only then the output value is 0. So, for the 4 inputs D0, D1, D2, D3, when the inputs are given, if they are 1, the input which has the highest priority is considered and the output corresponds to the value of the highest priority input. So, the logic expression can be directly read from the truth table or draw a K-map and reduce it and get the logic expressions. For the valid output V, it is high for D0 or D1 or D2 or D3 input. So, use an OR gate for that. Y0, the output is high when D1 is high and D2 should be low. So, D1 D2 bar or for D3, and Y1 is high for D2 or D3. So, the logic expressions are given here and from that draw the logic diagram. Next is decoders. They are nothing but the reverse of the encoder, that is multiple input and multiple output combination circuit where we have n inputs and 2 power n outputs or less than 2 power n outputs. And this is similar to a demux with the selector lines being considered as the input lines. And decoders are used in various applications. For example, to have a display in 7 segment LED, the code binary or BCD code should be converted to 7 segment code. So, a decoder is used in that case. They are used in counters, digital displays, so on. So, let us see how to design a 2 to 4 decoder. So, there are 2 inputs. If you have 2 binary inputs, the unique values we would have 4 unique values, therefore 4 outputs are available. First draw the truth table for the same 2 inputs. The combinations for that are 0 0 0 1 1 0 1 1, and corresponding to each combination a unique output is available. So, for 0 0 Y0 is high, 0 1 Y1 is high, 1 0 Y2 is high, and 1 1 Y3 is high, and from this draw the logic diagram. So, Y0 is A bar B bar, Y1 is A bar B, Y2 is A B bar, and Y3 is AB. Now, pause the video, design a 3:8 decoder. So, there are 3 input lines and 8 output lines. So, this is a truth table and logic diagram for a 3:8 decoder. Next, let us see how to implement logic expressions using 3:8 decoder. For this given logic expression, f is equal to sigma m of 1, 2, 3, 7. 1, 2, 3, 7 are the min terms for which the output is high. So, draw the truth table, and since we have 8 outputs, we need a 3:8 decoder, and the 3 inputs are A, B, C, and the output for which the min terms are 1 are all connected to an OR gate, and that gives a logic expression being implemented using the decoder. Pause the video, design a full adder circuit using decoders. So, to design a full adder has 3 inputs. So, we need to use a 3:8 decoder. There are 8 outputs. Draw the truth table using the 3 inputs, and then we have 2 outputs, sum and carry. Check the output for which the min terms are 1. So, write 2 expressions, one for the carry and one for the sum, and implement it using a decoder. Verify your answer. Next, we shall see magnitude comparator. A magnitude comparator is a combination circuit which compares 2 binary numbers and gives the result as to whether the number is greater than or equal to or less than the other. So, A and B are 2 binary numbers. They can be of any number of bits. So, here this is an n bit comparator. So, A can be of n bits and B n bits. The output A is less than B is high if A is less than B, and if they are both equal, this line is high, and if A is greater than B, the third output is high. So, let us see how to design a 1 bit magnitude comparator. So A and B both have 1 bit each. So draw a truth table considering all the combinations of 0, 0, 0, 1, 1, 0 and 1, 1. And we have 3 outputs, A greater than B, A equal to B and A less than B. So for first combination A 0, B 0, it is A equal to B is 1. When A is 0, B is 1, it is A is less than B. So that is 1, the other two are 0. And for 1, 0, A is greater than 1, so that output line should be high. For 1, 1, A is equal to B line should be high. So draw the K-map or read directly from the truth table. So for A is equal to B, we get A dash B dash plus AB, which is nothing but an XNOR gate. And then for A greater than B, it is AB dash. For A less than B, it is A dash B. So this is the logic diagram for the 1-bit magnitude comparator. And for a 4-bit magnitude comparator, IC 7485 is available. Now pause the video, design a 2-bit magnitude comparator. So here A and B, the two numbers, binary numbers have 2 bits each. So consider A1 and A0 for A and B1 and B0 for B. So the 4 inputs are A1, A0, B1, B0. Write all the possible combinations possible. The outputs are A is greater than B, equal to B or less than B, 3 outputs. Draw the truth table, get the logic expression and draw the logic diagram. So in this video, we have discussed about encoders, decoders, priority encoders and magnitude comparators. These are the references. Thank you.